The derivative can also be seen as a function. Let's write the definition of the derivative as a function of x. So f prime of x is the limit for h going towards 0, f of x plus h minus f of x divided by h. In that case, f prime becomes a function of x with its own domain and its own range, and this is the function, the derivative of f. So we have the function f prime who maps x onto f prime of x, given that this derivative exists. So this means f prime maps x onto f prime of x. Then we say that a function is differentiable at some point a if f prime of a exists. We can also look at differentiability on a set. So a function is differentiable on a set of points. Let's call this set S if it is differentiable for every point in the set. What now if S is a closed interval? So we have what if S is a closed interval going from A to B, for example. In that case, we have a problem because we cannot use the definition in our endpoints. In the endpoints, we cannot find a limit. We can only find a left limit or a right limit. And so we just make the substitution that we need. So in the left point, we will use a right derivative, and in the right endpoint, a left derivative. So we define on the one hand the left derivative. The left derivative will be used in the right endpoint, so it's the limit for h going to 0 but with values smaller than 0. So we approach from the left, f of x plus h minus f of x over h, and we use the right derivative in the other end. So the right derivative is the limit for h going to 0 but with positive values, f of x plus h minus f of x divided by h. Then we apply these formulas to find the derivatives in the closed interval. So b only has values to the left, so we will use a left derivative. And f prime of b becomes the limit for h going to 0, but with values smaller than 0. F of b plus h minus f of b divided by h. For a, we only have values larger than a, so we have a right derivative. F prime of a is the limit of h going to 0 with positive values, f of a plus h minus f of a divided by h. Take, for example, a look at the function square root of x. So f of x is the root of x. Where is f differentiable? Since the domain of this function is only the positive numbers, we will have to calculate the derivative in two parts. So the domain of f, domain is the part of R, so the values where the function is defined, goes from 0 to plus infinity. So the square root of negative values is not defined. And we will just have to define or calculate the derivative in two parts. You have a part where x is strictly positive, because this is the inner part of the domain. And then you have to look at the boundaries, so in the point x equal to 0. Let us start with the positive case. So here, the derivative f prime of x is just the limit h going to 0 of f of x plus h minus f of x over h. So it is the limit of the square root of x plus h minus the root of x divided by h for h going to 0. And to solve this, what we will do is we will multiply with the conjugate, so x plus h plus the root of x divided by the same thing, so we just multiply by 1. This limit then becomes the limit for h going to 0 of the absolute value of x plus h, but since x and h are positive, we are in a positive case, so x plus h minus x divided by h times the root of x plus h plus the root of x. Then we see that this one cancels out. We have an h which is left over, which we divide out with this h. And so we get, this is the limit for h to 0 of 1 divided by the root of x plus h plus the root of x, or it is 1 divided by 2 times the root of x. For 0, we have f prime in 0 is the limit for h going to 0, but with positive values, of the root x plus h, but x is 0 in this case, so the root of h, plus the root of 0 divided by h, so it is the limit h to 0 from the positive side of 1 divided by the root of h, or it goes to plus infinity. So we see now that the derivative is defined everywhere except in 0. So the domain of f prime is again the interval 0 to plus infinity, but this time 0 is not included. The derivative does not exist in 0. Hence, we say that f is differentiable, so differentiable on a closed interval ab if f is differentiable on the open interval ab, is left differentiable in b, so the right endpoint, and is right differentiable in the left endpoint a. Example: verify the differentiability of f of x equal to the absolute value of x. If we plot the function, we see that there is a corner in the point 0, and we will make a distinction between 3 cases. We will look at x strictly positive, x strictly negative, and then also what happens at the point x is 0, so where both parts of the function come together and make the corner. First, assume that we have x strictly positive. So in this case, if my absolute value of h is small enough, which we can always have because h is going to 0, then we know that also x plus h is positive. So we will need to know this in order to know what we do with the absolute value. If we then calculate the derivative, so f prime of x is the limit f x plus h minus fx divided by h to 0. Here we see this is the limit of the absolute value x plus h minus the absolute value of x divided by h towards 0. We now know that x is positive, so the absolute value of x is x. Same thing for very small values of h, which happens because h is going to 0. X plus h is positive, so we have just x plus h minus x divided by h to 0, and this limit is 1. If x is negative, so strictly negative, we make it the same reasoning. So if my absolute value of h is small, then x plus h will also be negative. And so f prime of x is the same thing, the limit of the absolute value x plus h minus absolute value of x over h for h going to 0. But now we know that these are negative, so h to 0. Absolute value of x plus h is minus x plus h, because we know that the absolute value of a negative number is the opposite of that negative number. So if we think about the negative value of minus 3 is 3, so it's minus of minus 3. So the absolute value of x plus h is minus x plus h. And then the absolute value of x is minus x divided by h. And so here we get -1 as a derivative. And then the final case, x is equal to 0. So here the derivative f prime of 0 is the limit of f of 0 plus h minus f of 0 divided by h for h going to 0. This is, if we write it out, the limit of the absolute value of h divided by h to 0. And then before we saw that we cannot calculate this limit as such, so we have to split it in a left limit, negative values. In that case, the left limit absolute value of h is minus h, and so the left limit is -1. And we need a right limit, so positive values of h, in which case that it is 1, so the right limit is 1. And so we have no derivative in this case. So here, this derivative does not exist because the left limit and the right limit, or the left derivative and the right derivative, are not the same. As such, we can say that the function f is the absolute value of x is differentiable on the entire real line except in the point 0. So it is differentiable for all numbers, but not in 0. And if we then think back on the definition of how that the derivative was introduced, this also means that there will not be a tangent line to the function in the point 0. Furthermore, we are able to prove that if f is differentiable at a point, then f is also continuous at this point. So, theorem: if the function f is differentiable at the point a, then f also has to be continuous in a. So it's no option, it cannot be otherwise. If it is differentiable, then it is continuous. The opposite does not hold. So because f is continuous does not imply that f is differentiable. Think, for example, at the absolute value. This is a continuous function. We can draw the line without lifting our pen, but in 0 the derivative does not exist. So this is a one-way theorem. Differentiability implies continuity, but continuity does not imply differentiability. We will not see the proof of the theorem. You just have to know that differentiability implies continuity, but that the inverse is not true. Other notations for the derivative. So there are a lot of notations, especially because the derivative was introduced in different sciences separately, so each of them had their own notation. So if y is equal to f of x, we have for the derivative f prime of x. We also write y prime sometimes. We write dy dx, so the derivative of y to the variable x. Sometimes it's also written as df dx or d dx f of x. In some cases we use a capital letter, so it is also written sometimes as the derivative of y towards x, so capital dx, the derivative to x of the function y, or the derivative towards x of the function f of x, or d of f of x if there is no confusion possible. So this notation is called the Leibniz notation, and it is the usual notation in physics. Here we omit the subscript if there is no confusion possible towards which variable we are differentiating. So we omit it if the variable of differentiation is clear. So there is no confusion possible to which variable we are differentiating. So these are all still functions. So this is the derivative of the function f, but written as a function. Sometimes we also have to evaluate this function, so we evaluate in a certain point. Let's call the point x0. The notations that we then use become f prime of x0, which is equal to dxf in x0, which is the same as y prime evaluated in x equal to x0, or dxy in the point x is equal to x0, or dxf f of x in x equal to x0, or which one did we not have, dy dx in the point x equal to x0. So here we have evaluated in this point, so this is no longer a function, but it becomes a value, a number.